Welcome to lecture 21. In this lecture, we're going to be talking about a few strategies for solving problems on caches, and we'll also look at a few sample problems. So before I do that, let me briefly recap three cache designs that we went through in the last few lectures. So the first one is a fully associative cache. In this cache design, a given cache block can be stored in any one of the cache lines in the cache. So for example, in this picture, I have 4 cache lines, and a blue cache block can be stored in any of those 4 cache lines. Now the downside of this is that I need to do a lot of tag comparisons. So if I have 4 cache lines, then to look up any given address, I need to perform 4 tag comparisons to figure out if that address is present in the cache or not, meaning if it is a cache hit or not. The upside is, of course, that because I have this luxury to store a cache block anywhere I want, generally a fully associative cache would give you a higher cache hit rate compared to the direct mapped cache and the set associative caches. So the direct mapped cache is the most restrictive in terms of where you can store a cache line. It gives you exactly one choice. So in this example, I have 4 cache lines. Each of them is part of a different cache set. Each cache set in a direct mapped cache has exactly one cache line. So in the direct mapped cache, a given cache block can be stored in exactly one cache line, and that can often lead to a lot of conflict cache misses, because now several cache blocks that map to the same cache line can compete with each other. As a result, they can kick each other out of the cache, leading to a number of conflict misses. So in this example, the orange cache block can be only stored in the orange cache line. The blue can be stored only in the blue cache line. The pink can be stored only in the pink cache line, and so on. Now, the number of bits that you need for selecting which block to store a given cache block depends on how many cache lines you have. Another way to think about it is each cache line is really part of a set, and the line index or the set index is selecting which set to store that cache block in. Again, a set in a direct mapped cache has exactly one cache line. Okay. In the case of a set associative cache, a set contains as many cache lines as the number of ways. So for example, in the case of a two-way set associative cache, then each set has 2 cache lines, like I'm showing here in this picture. So what I'm showing here is a two-way set associative cache. So I have way 0 and way 1, and they both are part of the same set, which means a given cache block that maps to a set can be stored either in way 0 or way 1. So I have 2 choices now. As a result, I can have a better cache hit rate than a direct mapped cache, because this two-way set associative cache would eliminate some of the conflict misses that you would endure in a direct mapped cache. Now the set index is again going to be determined by how many sets you have. The only difference now is the number of cache lines within a set is different. Alright, so now let's go through a few general strategies for how we can solve problems in caches. The first thing to remember, and this is a common source of confusion or question that we get, is who defines the address size? So the address size is defined by the ISA. So that's why we talk about 32-bit ISA or a 64-bit ISA, etc. So what that means is the address size is 32 bits or 64 bits, depending on which ISA you're talking about. And that information is visible to the programmers and the compiler. Now the cache design, on the other hand, the details of that is hidden from the programmer and the compiler. As a result, the cache design details are not specified as part of the ISA. So when you are given an address, and for a given cache design, you have to interpret that address into these three different fields: tag, line index, and block offset. That interpretation is specific to a cache design. And so it's a cache that takes the address and partitions them into those three fields. The details of how to do that is invisible to the programmer and the compiler, and they're not really part of the ISA. And that's why a cache design can vary from one processor implementation to another, even though they both may support the same ISA. Another common source of confusion is in understanding the difference between the byte addressable versus word addressable ISA and its impact on how to compute some of the details for cache configuration, in particular block offset. So let me briefly recap what byte addressable ISA versus word addressable ISA is. So if an ISA is byte addressable, what it means is any given address refers to a memory location that stores exactly 1 byte of data. Okay, so if I have a memory and if I address it sequentially through addresses ranging from 0 to n, each address refers to a memory location that stores exactly 1 byte worth of data. In the case of a word addressable ISA, each address refers to a larger data item, and that size is the size of the word. So instead of a byte, it would be a word. Now you may question, okay, what is going to be the size of the word? Now, in common practice, a word is usually the same size as the number of bits that you're used to describe the ISA. So it changes from one ISA to another, unfortunately. So byte is just 8 bits no matter what ISA you're talking about. But a word, the size changes from one ISA to another. So if I'm talking about a 64-bit ISA, a word is going to be of 64 bits in size. If I'm talking about a 32-bit ISA, a word is going to be 32 bits in size, right? And so you need to factor that into the size computation. Now, why are we talking about these differences? Because you'll see that in some of the problems posted online from previous exams, they may tell you whether the ISA is byte addressable or word addressable, and that has a significant impact on how we compute the size of the block offsets. Let me explain. So block size is usually defined in terms of bytes. So I may say my cache block size is 256 bytes. Fine. Now to figure out what should be your block offset size, so far what we've been saying is just do a log to the base 2 of the block size that is given to you. So if it is 256 byte block, say it's 256, and then you will figure out that, oh, it's 8 bits. Now that's a reasonable assumption to make, provided that each individual byte within your block is addressable. Meaning, if it is a byte addressable ISA, that assumption is a valid assumption. However, if your ISA is word addressable, then you have to remember that I can only address memory locations in chunks of word. I cannot address individual bytes within a word. So therefore each address refers to one word in a cache block. So therefore my granularity is now much larger, which is a word. And now I have to think about the block offset as how many bits do I need to distinguish the different words in that block, right? And so one has to then figure out how many words do I have in a 256 byte block. right? So all that matters is how many addressable data items do I have in a cache block. That's what matters when you're trying to compute your block offset. So if it is a byte addressable ISA, the number of addressable data items is exactly same as the number of bytes, and that's why this computation was correct. But now if it is a word addressable ISA, you need to compute the number of words in a block. Now for this example, it would be 256 bytes divided by the size of a word. The size of a 64-bit word is going to be 8 bytes. So I would have a total of 32 words in this block. So if I have only 32 addressable data items, then my block offset has to be only of size log to the base 2 of 32, so it's going to be 5 bits. So for the same block size and for the same address size, right, so same cache block size and same address size, 64 bits, I can end up with two different block offset sizes depending on whether it is a word addressable or byte addressable. So that's something to keep in mind when you are parsing through the cache problems. So I talked about a few equations in the last lecture. I would like to go through them again because it's quite important and useful when you're looking at cache problems. So the first thing is the number of cache lines is same as the number of cache blocks. So these two terms are often used interchangeably, but to me, a cache block refers to the cache block of data. Cache line refers to the hardware structure that stores the cache block along with the metadata such as the tag, LRU bits, and the valid bit. But in terms of the numbers is exactly the same, and that's one of the reasons why they seem to get used interchangeably. The way to compute the number of blocks, or the number of cache lines, is by dividing the cache size divided by the block size. That's pretty straightforward. And the number of block offset size would depend upon the block size. So log to the base 2 of the block size is going to be a block offset size. Alright, so now we need to compute the number of sets. The easiest one is a fully associative cache because the number of sets is always 1. Doesn't matter what your cache size is, doesn't matter what your block size is. Number of sets in fully associative cache is always 1. Why is that? Well, the way to think about it is in a fully associative cache, all the cache lines are part of one single set. And a cache block therefore can be stored anywhere within that set, which consists of all the cache lines in the given cache. So the other extreme, we have the direct mapped cache. Again, it's fairly easy to compute because all you need to do is to take the number of blocks and then you know the number of sets because they both are exactly the same because the number of cache blocks per set is 1. Now let's talk about two-way set associative caches. In this case, the number of cache lines per set is 2. So I have to take all the lines I have, divide them by 2, and then I will be able to compute the number of sets. So every set will have half the number of, the number of sets will be half as many as the number of lines. I can generalize this and say, well, if I have an n-way associative cache, then I would divide the given lines by the number of ways to compute how many sets I get, right? So once you have figured out the set number of sets, computing the set index size is trivial. Just take a log to the base 2 of the number of sets. And once you have your block offset size and the set index size, you subtract those from the given address size. Again, that's defined by your ISA. Then you get your tag size. Let me talk about the 3C problem first before I talk about the cache performance. So in the case of a 3C problem, it's common to think about to recap what we talked about, 3 types of cache misses. we want to understand the type of cache misses that we experience for a given cache. So I take the cache, I take a look at its geometry, and you look at the address sequence X, Y, Z, right? And then you ask yourself, oh, I see some hits and some misses. And you want to understand why you are experiencing some misses. What is the reason for those misses? And to understand what type of misses you are incurring, you need to simulate not only the given cache to figure out what these hits and misses are, but you also need to simulate two more caches, an infinite cache and a fully associative cache. Let's see how to use those two caches to classify the misses that you observe in the given cache. Okay, so the question we are asking is, you're given a cache, let's say two-way set associative cache with some sort of block size and some number of cache lines. So you know what your cache looks like, and you went and simulated it. And after simulating it for an address sequence, you were able to figure out which addresses were hits and which addresses were misses, and you're asking yourself what type of a miss is each one. And to answer that question, the first thing you need to find out is this miss for a given address also a miss in the infinite cache? And if the answer is yes, then you would say it's a compulsory miss. And the way to think about it is, if a miss in the given cache is also a miss in the infinite cache, then no amount of capacity or no amount of associativity is going to turn this miss into a hit, and therefore the miss is compulsory. And the only way in which you could reduce compulsory miss is by increasing the cache block size to exploit more spatial locality. Okay. Now let's say the miss turns out to be a hit in the case of infinite cache. So then what do? Well, you ask the second question. Is that miss that I saw in the given cache, is that still a miss in the fully associative cache? And if the answer is yes to that second question, then you will say, well, then the miss that I saw in the given cache is actually a capacity miss. Why is that? Well, even with the best possible associativity, which is a fully associative cache, I still incurred a miss. So the only way in which I could solve this problem is perhaps by increasing the size of my cache. Now this is a little bit of imprecise statement to make, because in the case of a fully associative cache, I need to assume a replacement policy, typically an LRU policy. So the miss that you may be encountering could be because of the replacement policy, but we're going to make approximate assumption, if you will, to sidestep that issue and say, well, if I see a miss in the fully associative cache, then I'm going to assume it's a capacity miss. And that's a fair assumption for the common case, because you're assuming an idealistic situation with respect to the associativity. And so so you can say that, well, the reason why I got a miss is really because of lack of space, right? Not necessarily because I had a poor replacement policy. All right, so now let's say you found out that the miss in the given cache is not a miss in the infinite cache, not a miss in the fully associative cache. Then you're left with only one choice, which is the conflict miss, right? Because it tells you that it's not a capacity miss, because it was actually a hit in the fully associative cache. And so the reason why you ended up with a miss is because you reduced the associativity to something smaller, maybe a two-way or a four-way set associative cache or an eight-way set associative cache. And so if you were to increase the set associativity, then maybe you may be able to get rid of this miss. Okay. So to summarize, you take the given cache, simulate it for the given address sequence, and figure out which one is hit and which one is miss, which addresses are hits and which addresses are misses. And to figure out whether those misses are to figure out the type of those misses that you just discovered, you need to simulate two more caches. The first cache is the infinite cache, but you need to assume the same block size as the given cache. And the second one is a fully associative cache. Also assume the same block size, but now you're going to have a limit on the size as well. And so you go and simulate those two caches, figure out what the hit and misses are. You take all that information and then go through this algorithm that we just went through, and then you'll be able to classify the sequence of misses that you observed for the given cache into one of these three types. Now, I talked a lot about simulating caches, and you may be asking yourself, what do I mean by simulating a cache? So a cache simulator, essentially what it does is, for a given cache configuration, right, for a given cache size, associativity, block size, etc., it abstractly models that cache. I'm representing that abstract model here. And then for a given address pattern, the given address pattern, the cache simulator tells me which one is a hit, which one is a miss, and so on. So cache simulator basically says some of them are hits, some of them are misses, and so on. I'm just randomly assigning these roles. They don't have any meaning, right? But basically a cache simulator for a given address pattern will be able to say which one of these addressees. So this is the address pattern. So this is the address pattern, and the cache simulator computes whether each address in that sequence is a hit or a miss. So that's what a cache simulator does for a given cache configuration. So in order to do that simulation, what the cache simulator has to do is it take each address and split that into these three fields. And we talked about how to split a given address into these three fields before. And then model the cache. Now, one of the tricks that you want to use is when you're modeling a cache after this point, once you have computed what your tag and set index is, then that information alone is sufficient to then go and simulate the cache. I don't really need the block offset. In fact, I don't need the data, nor do I need the block offset after that point, because the state of the cache only depends on the tag and the set index. The block offset is only going to be used to access a byte in a given data, which is very important in the processor to grab the data, but to simulate a cache and figure out hits and misses, you don't really need that. The final thing to implement while you're doing a cache simulation is to keep track of the LRU rank for the cache lines. And the algorithm that we talked about for that is for the cache lines within a set. Let's say you have 4 of those. I need to keep track of a counter. I'm going to call that as a LRU counter. And that counter is going to keep track of the LRU rank. Higher the rank means it's least recently used. Higher the rank is bad. Now when I access a cache block within the set, I'm going to set its rank to 0, meaning it's the most recently used block. And then I have to increment the counter for all the other cache lines. And when I have to pick a victim, I'll pick the cache line with the highest LRU counter. So that's one way to implement the LRU rank and replacement policy. And keep in mind that other replacement policies do exist. Another one would be most frequently used policy, in which case you would say if a cache block is most frequently used, then I don't want to evict it, etc. So I don't want to go into the different replacement policies, but the point here is that when you're simulating a cache, you need to simulate the LRU rank for the cache lines within a set. So one thing I need to clarify here is that in the fully associative cache, you will be maintaining the LRU rank across all the cache lines because all the cache lines are part of one single set. But in the case of a set associative cache, that is not true. So let me say that I have a 4-way set associative cache, let's say. So these little boxes that I'm drawing each represent a cache block within a set. So I have 2 sets here, and I have 4 ways. And the point I was trying to make is that the replacement policy need to bother about only the blocks within a set. So the LRU rank will be maintained across the blocks within each set. So let's say that I have accessed all these cache blocks, and it turns out that the least recently used cache block across these 4 happens to be this one, so then I will choose that to be evicted. Now it may be the case that set 1 contains really old cache blocks that the program has rarely ever accessed, right? And so in that case you would say, well, that's not a good idea. Why not replace one of these really old cache blocks in set 1? Well, you can't do that, because in the case of a set associative cache, for any cache block you have the option to store that cache block within one of the 4 cache lines within the set where you can store that cache block in, right? So LRU across the sets doesn't make sense. You need to implement the LRU policy within a cache set. Alright, so in addition to being able to simulate a cache, it is important to understand how to reason about a cache's performance. And we talked about this metric called average memory access time in the first lecture on caches. And I would like to clarify one common source of confusion that you may have when you look at the problems from the previous semesters. And that is due to the difference in assumption we make about the memory latency. Now let me talk about the most intuitive way to calculate AMAT, and then I will clarify this variance. Now, one important thing to understand is every memory access first accesses the cache, and if it's a hit, you're done. But if it is a miss, then you go and access main memory. So when you're thinking about average memory access time, you're trying to ask yourself, on an average, how long does a memory access take? Well, if all of them are cache hits, then the average memory access time would be just the cache latency. But that's of course not true, because for some fraction, which is defined by the cache miss rate, for some fraction of memory accesses, I would have to additionally incur the latency of accessing the main memory. So therefore, the way to calculate the average memory access time is by adding cache latency with memory access latency and multiplying that with the miss rate. That seems fairly intuitive, right? Now, this is true, this way of calculating AMAT is correct only if we assume that the memory latency does not include the cache access latency. Now that's a reasonable way to think about it, right? So I would specify, okay, what's the time it takes to access main memory, what's the time to access the cache, so you can plug those numbers in and compute AMAT. That's correct. But sometimes in a few problems, they may state that, assume the memory latency includes the time to access the cache. So now what that means is, for when I say some fraction of cache misses, I incur the latency of memory. That latency includes the cache access latency and the main memory latency, right? So it already includes the cache access latency, and therefore you don't need to double count it, and that's why it's important to attribute the cache only latency to the fraction of accesses that are cache hits. So the fraction of accesses that are cache hits would endure cache latency. The fraction of accesses that are misses would endure the memory latency, which includes the cache latency, and that is consistent with our view that every memory access first checks the cache and then goes to the main memory. Okay, so look out for this assumption when you are looking at the cache problems. Does the main memory latency include the cache access latency or not? If it doesn't include, use this equation. If it does include, use this equation. And we'll always try to make it clear which one of these assumptions we are making in our problems. Okay, now let's take a look at a few sample problems on caches. So in this problem, we'll try to understand the difference between a byte addressable ISA versus a word addressable ISA. So in this case, the problem says the ISA is word addressable, different from the problems in caches that we have talked about so far. And the cache is a fully associative cache of size 64 kilobytes, and the block size is 32 bytes, not words, 32 bytes. The question asks you to determine the size of the block offset and tag. So now let's think about the block. So we are given that it is of size 32 bytes. Now for a byte addressable ISA, I would say there are 32 different addressees that can refer to this block, right? But in the case of a word addressable ISA, we'll have to first think about how many words are there in this block. So in a 32-bit word addressable ISA, it's assumed that the word is 32 bits, which is 4 bytes. So if a word is 4 bytes, then how many words do I have in this block? Cache block, 32 by 4, so that will be 8 words. So if there are 8 words in a block, that means I need 3 bits in my address to index into that block. So my block offset is going to be of size 3 bits. The total size of my address is 32 bits. Now I need to figure out how many bits do I need for my set index. Set index, it depends on the number of sets in the cache. For a fully associative cache, the number of sets is always 1. And if I have only one set, I don't need an index to figure out which set I can store my cache block in. So you don't have a set index as part of your address. So we have already calculated the block offset, which is 3 bits. So the remaining is going to be the tag. And so 32 minus 3, so 29 bits are for tag. So the size of block offset is 3. And the tag size is 29 bits. Alright, so now let's take a look at a different problem. So this problem is on understanding the impact of cache performance on CPI. So we have computed CPI in the past for the different data paths. So now we are going to try and use that same method of computing CPI, but account for the cache performance. So the way to go about solving such problems is to first understand what is the CPI composed of. Now the CPI is has several parts to it, but on average what we are asking is what is the average clock cycle that an instruction would take. So in this example, we are given that we're given some information here, so then we can compute based on this information what the CPI would be. So it's a pipeline data path, and so the CPI is going to be 1 in the ideal case. But then we need to account for the different types of hazards that we will see. So the different types of hazards are, you have to have some penalty for data hazard, some penalty for control hazard. And now we also need to have penalty for iCache miss rate and data cache misses. So, and keep in mind that every instruction needs to access the instruction cache to get the instruction. So every instruction is potentially can miss the cache, right? The instruction cache. The data cache, on the other hand, is only going to be accessed by loads and stores. Okay, so these are the 4 components, and now we have to think about what are these 4 components for this given problem. So the data hazard penalty is due to the data dependencies, the read after write dependencies. And so in a pipeline data path where you are assuming full data forwarding, you have a penalty only for the load instructions that are immediately followed by a dependent instruction or followed by an immediate use. Okay, so for this problem, we are given that there are 15% of instructions are loads, and of those loads, 50% of them have this pattern where it's immediately followed by a use. So the data hazard penalty would be I have 15% of loads, of them 50% have an immediate use, and the penalty when this happens is 1 cycle, because you need to stall the pipeline for an additional cycle. And the control hazard is going to be only for branches. So I have 20% of instructions are branches. Of those, 40% of those branches are taken. So now you need to think about what fraction of branches are going to be mispredicted. And for that, you need to know what type of a branch predictor we are assuming. So the branch predictor is assuming that all the branches are not taken. So whenever a branch is taken, it would be a mispredicted branch. So 40% of the branches are mispredicted, and whenever that happens, I have to incur a 3 cycle penalty. So now finally I have to compute the instruction cache misses and data cache misses. So like I said before, every time when you execute an instruction, you have to fetch, decode, execute, mem, and write back, right? The fetch stage fetches the instruction from instruction cache. Now we are told that if there is a cache hit, it's always 1 cycle. So what that means is the fetch can finish in 1 cycle, so there is no need to add any additional penalty. But 3% of the time, you may have an instruction cache miss. And when that happens, you have to go to the main memory. So 3% of the time, that is 0.03 times, I would have to go to the main memory. And if I do go to the main memory, I have to incur this latency. Now I need to translate this latency into a memory cycle, clock cycle, so that I can plug this into my equation. So for now, I'm just going to assume it's m, and then I'm going to come back and compute what that m is going to be based on this main memory latency that is given to me. And so finally, I have the data cache miss penalty, and for that I need to consider only the loads and stores, so which is 15% of them are loads and 20% of them are stores, and so together it's 0.35. So for 35% of instructions, I may miss the data cache 6% of the time, and when that happens, I have to go to the main memory and incur a latency of m, which I have not computed yet. Okay, let's compute the number of cycles to access the main memory. So we are given that it takes 100 nanoseconds to access the memory. Now we need to convert this into processor clock cycles. To do that, we need to look at the processor clock frequency and figure out what is the clock period, or rather clock cycle time. So the way to compute clock cycle time from a clock frequency is clock period is 1 over clock frequency, right? So clock time is 1 over clock frequency. So frequency says I can switch 500 times 10 to the power of 6 times within a second. So now if you want to compute how many seconds or how much time it will take for every cycle, you need to do 1 over that. So that's 1 divided by 500 times mega is 10 to the power of 6. So you have 1 over 10 to the power of 6, which is equal to 1000 divided by 500 nanoseconds, because nano is 10 to the power minus 9. So this equation works out. So that will be 2 nanoseconds. So therefore clock period for this particular processor is 2 nanoseconds. So if one clock takes 2 nanoseconds, then if I have 100 nanoseconds, how many clock cycles would that be? So that will be 100 divided by 100 nanoseconds divided by 2 nanoseconds. That will be 50 cycles. So the main memory latency is 50 cycles. So that's what we had used as M here. So M value is 50 cycles. So I can plug that 50 in there. So instead of M, it would be 50. And once you compute this equation, you would have figured out what your CPI value is. Okay, we have another problem on caches. In this problem, we are asked to assume the CPI is 1 as long as your cache hit rate is 100% and the cache latency is 1 cycle, which is easier in some sense because you don't have to account for data hazard penalties and control hazard penalties. You only need to worry about the remaining cache miss penalties and its impact on CPI. So the CPI equation would be 1 plus instruction cache penalty and data cache penalty. So we are also given that the processor clock frequency is 200 megahertz. It's often useful to think about clock cycle time. So the clock cycle time will be 1 over 200 mega. Mega is again 10 to the power of 6 hertz. So it's 1 over 200 10 to the power of 6 seconds. So that will be 10 to the power of 3. That's 1000 divided by 200 nanoseconds. So that would be 5 nanoseconds. Okay, so we have some information on our hand. So let's go and look at what the problem asks us to do. So it asks us to consider 2 different changes to the hardware and reason about which one will get higher performance. So to compute that, we are going to compute the CPI of each of these options. So the CPI of option 1 is again going to be 1 plus instruction cache penalty. So in this case, we are asked to double the clock frequency. So doubling the clock frequency is not going to change the fact that you need to access the cache for every cycle, every instruction, because recollect that fetch, decode, execute, mem, write back are the 5 stages that you need to go through for every instruction. So the fetch stage involves accessing the instruction memory, and so for every instruction you access the instruction memory. And for this problem, the instruction cache hit rate is 95%. So which means the penalty would be 1 minus 95%, that is 1.05. And now you need to multiply that with the memory latency. So the memory latency for this option is 40 cycles. So we'll come back to that in a moment. And then for the data cache, we are asked to assume that 30% of instructions are loads and stores. So of the 30% of loads and store instructions, how many of them miss the cache? That depends on the data cache miss rate. That is 100 minus 90, that's 10%. So 10% of all the loads and stores miss the cache and go to memory. And if you go to memory, it's going to cost you 40 cycles. Alright, so you may have noticed an inconsistency here with respect to the main memory latency being 40 cycles. In the previous slide, we said in the baseline it is only 20 cycles. So why is it the case that when you double the clock frequency of the processor, the main memory latency increases to 40 cycles? The answer is the main memory latency doesn't really increase. It stays a constant in terms of the actual time it takes to access the main memory, right? So what changed is the time of the clock period. So when I say that the main memory latency is 20 cycles and the processor clock frequency is 200 megahertz, then the main memory latency is really 100 nanoseconds, right? Now that does not change when I double the clock frequency of the processor. So now when I double the clock frequency of the processor in option 1, now my main memory latency is still 100 nanoseconds, but now my clock frequency has gone up, and so my clock frequency has doubled. So when my clock frequency doubles, my clock period would reduce by half. So before it was 5 nanoseconds, so now it would be 2.5 nanoseconds. So this would give me 40 cycles for main memory latency. Okay. All right, so now let's compute the CPI for the option 2. So again, it's going to be 1 plus, for every instruction I have to incur the I have to access the instruction cache. So in option 2, I'm going to double the size of my caches. So when I double the size, the cache hit rate goes up. So instead of 5% miss rate, now it's only 2%. Now the main memory latency is the old main memory latency because the frequency of option 2 is same as your baseline. So it's 20 cycles. And then I have still 30% of instruction cell loads and stores, and the miss rate has gone down because I doubled my cache size, so it's gone down to 5%, and the main memory latency is the old main memory latency, so that's 20. So now if I do the math, it will be 4.2 and 1.7. So you will see that the option 2 is clearly worse than option 1 in terms of CPI. But when you're reasoning about performance, CPI is only part of the equation. What really matters is the execution time of a program, and that depends on CPI, but also you need to multiply that CPI with the number of instructions that you're going to execute, right? Because CPI is clocks per instruction. So if you have to multiply by number of instructions, you'll get the total number of clock cycles. But that again doesn't tell you the whole story because it's just expressed in terms of the clock cycles. What we want is time. So for that you need to multiply this with clock cycle time. Now let's see what that is for option 1. So for option 1, the CPI is computed as 4.2. We don't really know the number of instructions because we don't really have any program to reason about this. So I'm just going to assume it's n, and the clock time, like we said, has actually gone down for option 1 because the whole point of option 1 is to double the clock frequency of the processor. So it went down to 2.5 nanoseconds. For option 2, you'll have much better CPI. Instruction doesn't change, but the clock cycle time, however, is the baseline processor's frequency, which is 5 nanoseconds. So now if you do the math, this comes to 10.5 times n. This comes down to 8.5 times n. So you will notice that option 2 is still the better option, but now we can confidently say that option 2 is better, but not as as good as it was before, because 4.2 is almost 3 times that of option 2, but the performance difference is much more tighter than what we originally thought it would be. And the reason for that is the benefit of option 1 is expressed in terms of the clock cycle time, whereas the benefit of option 2 is expressed in terms of the CPI, because we were able to reduce the CPI by increasing the cache hit rate. Okay, I saved the best for the end. Reverse engineering the cache can be fun. So in such problems, you're typically given not the entire cache configuration, but some parts of it. And then you would be given a sequence of addressees and their hits and misses. So it's as if someone took a sequence of addressees, wrote a cache simulator, figured out what the hits and misses are, and they are not giving you the exact cache configuration, and you're asked to figure out what the configuration should be. So the address pattern and the hit and misses typically have enough constraints so that you can figure out the rest of the parameters. So the key is to really come up with those constraints, and from those constraints you can derive the cache parameters. So let's see how we can go about deriving those constraints for this problem. So we're given the cache size to be a 512 bytes, and the address is 12 bits and nothing else. We have to figure out the block size, associativity, and the number of sets, all from this data that we are given here. Okay, let's see how to go about figuring out the block size first. So let's now look at the first few cache accesses. So you'll notice that the first 3 out of 4 accesses, they all have the same prefix to their address. Maybe they all came from the same block, and if they did, then maybe we could conclude something about the block size. We also see that couple of them were misses, and the third one was a hit. So maybe the miss, the second axis being a miss, can tell us something about how what is the largest size possible for a block, because if the block was really big, then given that the prefix were somewhat the same, it would have been a hit if you were able to exploit spatial locality. So that should give us an upper bound on what the cache block size should be. And the second axis, or sorry, the third axis is a hit, and this address was not accessed before. So that means you're exploiting spatial locality. So this should give us a bound on what is the smallest possible block size. So between those two constraints, maybe we could figure out what the block size should be. Okay, so now let's start off by converting these 3 addresses to the binary format. So the given address is in hexadecimal, obviously. So you have so I've converted the 3 addresses to the binary format, and we know that this address is a miss, this address is a miss, and this one is a hit. Now you will notice that the prefix for the first 2 addresses are the same, except until this point. After that, they diverge. So given that the second axis is a miss, it clearly means that the second address is not part of the same block as the first address. Now if I had chosen let's say a block of size 2 to the power of 5, meaning my block offset is 5 bits, and then I would draw the partition here and say, well, my tag is going to be whatever it is to the left, and you will notice that the tag is exactly the same. So if the tags are same, then I would have observed a cache hit because they are next to each other. Clearly they are not part of the same block, which means they should have different tags which means clearly the block size has to be smaller than 2 to the power 5. Perhaps the block size cannot be bigger than 2 to the power 4. So from just these two axes I can infer that the block size should be less than or equal to 2 to the power 4. So now let's see if I can derive one more constraint. If I look at the third axis, that turned out to be a hit. Third meaning I'm not worried about this one in the middle. I'm just considering 1, 2, and 3 here. So the third axis here is a hit, and which means that it must be part of the same block as one of the previous two addressees. Now the question is, which one could it be part of? Well, we need to see which one it shares the longest prefix with. It turns out that it shares the longest prefix with the first address, and so maybe it is part of that first block. And that means what if you draw the boundary over here and say my 4 bits is my block offset, and you will see that the block offset cannot be any smaller than 4 bits, because if I draw a line with just 3 block offset, then you will see that the prefix doesn't really match, which means the tag doesn't really match with any of the previous two accessees. So given that this is a hit, this is clearly not possible. So therefore it has to be, the block has to be at least as big as 2 to the power 4. So now if you combine these two constraints, then you will get the block size to be 2 to the power 4, which is 16 bytes. So once you figure out what the block size should be, then we can compute the total number of blocks very easily. So that is 2 to the power of 9 divided by 2 to the power of 4. So that is 32 lines. So your cache has 32 lines. So 512 byte cache, because each block size is 16 bytes, you have 32 lines. So now let's figure out what should be the associativity of this cache. So we know that in addition to 512 byte cache size, each block is of size 16 bytes. Now to figure out the associativity, again, there is no standard procedure that you could use, but one strategy could be that you try the direct mapped cache, see if the direct mapped cache is consistent with the hit-miss pattern that is given to you. If not, try 2-way, then if not, try 4-way, and see if you can find contradiction for any one of those designs. The moment you find a contradiction, then you can discard it. So you don't have to simulate for all the addressees, you just need to simulate enough to discover a contradiction. And when there is a contradiction, you know that it's not the right solution. So now let's try the direct mapped cache and see if it would work. So for a direct mapped cache, we have to figure out the set index and the tag. So we know that the block offset is going to be 4 bits. And we also know that the number of cache lines is 32. So we have 32 cache lines in a direct mapped cache, which means log to the 32 number of set index, so that will be 5 bits, and the remaining will be tag, so it's a 12-bit address, so that will be 3 bits for the tag. Okay, so now I can try to simulate my cache for the direct mapped cache with this information. So it's worthwhile to compute my set index for tag and set index for these addressees. So that this would be 0, 0. So I have converted the addressees into binary form, but I have not translated the last nibble, because I know that the last 4-bit is a block offset, and the block offset doesn't really affect my cache hit or miss rate. So I have only translated the first 2 bits, first 2 nibbles. So this would be this, and this would be this. and that's enough for me to figure out my tag and set index. So my set index has 5 bits in it, so these would be the set index and the first 3 bits would be the tag. So now let me simulate my direct mapped cache. So I will see that you'll see that the first one, the set index is 10001, so that is and you'll also notice that the third address has the same set index as the first address, and the fourth one also has the same address. So now if it was a direct mapped cache, then these two addresses would map to the same set index, which is 1001, right, which is really 17. So if this was a direct mapped cache, then you can conclude that because of the fact that this address will map to the same set as this address, it would have evicted this address, and so therefore let's simulate this cache and see what will happen. So I have the tag 1 after executing the first instruction. I'm not going to bother about this one for now because it has a different set index, and this index has a tag of 2, so this would have evicted it, so it will be 2 0 1 0. And then for this axis, again the set index is same, but the tag is 1, which I had evicted, so it would be a cache miss. So if I use a direct mapped cache, this axis would be a cache miss, and that's a contradiction. So therefore I can rule out that my cache is not a direct mapped cache. So I now need to try out a two-way set associative cache. So in the case of a two-way set associative cache, I would not have 32 sets. I would have half of that, so that will be 16, which means that my set index would be just 4 bits, which kind of makes it easier to know what the set index is, because this is going to be my set index. So given that is my set index, let's see if I can simulate my entire address pattern and make sure that it is consistent with the cache configuration that I am discovering. Okay, so again I have written just the first and the second nibble. I've ignored the block offset when I translate it into the binary, because the block offset doesn't really help me simulate my cache. Alright, so my set index is defined by my the nibble in the middle. So I would have set index 1, it has a tag 3, and then set index 0, tag 3 again, so both of them are misses. So far we are good. And then we have a set index 1, tag 5, so the set index 1 would map to the same set, but however it's a two-way set associative cache, so I have 2 cache blocks per set, so that means I have another cache line that maps to the set 1, so I can store this tag 5 in the second way. And then if I simulate my next address, it will map to the same index, and I will notice that it is actually a cache hit. Great, it's consistent. Now my address 72D, it will map to index 2 with the tag 7, and then 72F, which will also map to the same index, same tag, so that will be a hit, and it is consistent. And then I have set index 2, tag 3, set index 2 tag 3, I don't have it, so it has a miss. Set index 2 tag 5, again this is a miss. So so this means I have to evict a cache block. I have to evict the least recently used cache block from the set 2. We just finished accessing the tag 3, so address 7 is the least recently used, so I'll have to evict that, and I replace it with the new tag 5, and then I finally access the last address, which is also set index 2 and 7, which we just happened to evict. So it turns out to be a miss. Again, it's consistent. So we just finished simulating a two-way set associative cache, and it seems to work well. There is no contradiction at all. So we can conclude that this cache configuration is a valid configuration for the given problem. Now, just for fun, we may want to double check and make sure that we got it right. And if we got it right, then higher associativity should result in contradiction. So after two-way set associative cache, we can try four-way set associative cache. So if we were to try four-way set associative cache, we can see if any one of the misses would have turned into a hit. And as we were going through this exercise, you would have noticed that this cache block at the end, we had accessed it before, right? And so it would have been a hit if not for this conflict that we had between the tags 5 and 7. And so if I had a four-way set associative or a three-way set associative even, then it's quite possible that it's possible that 7 and 5 can both be stored at the same time. And so you can go through this exercise and figure it out by yourself. You'll see that in a four-way set associative cache, this access would turn out to be a hit, and that would be a contradiction. So from that exercise, we can get more confidence that the given problem, the cache in the given problem is two-way set associativity. So we figured out that it's a block size is 16 bytes and set associativity is two-way. And given that information, then we can figure out the number of sets. That is simply the 16 sets, because we have 32 lines.